Hi, welcome back to the Chicago Statistics Lecturing Series. And we are at the second unit. We talk about the random variables and their distributions. Okay, so the last video we talk about is the random variable, how to define the random variable, and we define the discrete type of the random variable. So for this video, we are going to talk about how about if your random variable is continuous? Then what is the probability density functions and what is the cumulative distribution function for the continuous random variables here? Okay, so let's take a look here. And, let's try to do a brief review what we learned for the discrete, right? So if you remember, so we talk about the random variable x. If x is discrete, that means the value of the x is it's countable. You can say x equal 1, 1.5, or 2, 2.5. So it's very, so there's nothing in between, right? So if it's a random variable, it's discrete, like with the example we did, yes, you toss 3 coins, the number of head, right? So then in the previous, we said, okay, so for the random variable, discrete random variable, if you order to take a look at the distributions and probability distribution, we have these tables, right? So we have this is x and the px. Then you put the different values of your random variable x and the different probability. So this is what we call this the probability distributions, right? So the probability x is the value, is a probability for your random variable x equal to a specific value. So this is what we did for discrete. And so today we're going to talk about is continuous. So we know for the continuous here, all right? So for the continuous, what's that mean? We talk about the discrete and continuous. We said the continuous is the random variable. You cannot, there's always the smaller units in between. Like we talk about the time, right? So like how many hours. So even right now you say the seconds, right? You can say the hour, minute, seconds. But in fact, we can divide the time into the smaller and the small units. We just don't have the, sometimes we don't have the units to measure it, but we know we can continue to divide it. So you cannot exactly say, I complete this task in 2 hours. Because how do we know it's not 2 hours and 1 second? How about it's not 2 hours and 0.1 seconds, right? So that's why we said this is what we call is a continuous type of the distribution, the random variable. So if a random variable is continuous, then we know that when the probability of the x equal to some specific value is meaningless, right? So it will be 0. Why is 0? Like I said, you cannot say I finished this job in 2 hours, right? Because it's not exactly equal, because 2 hours, how do you know it's not 2 hours, 1 seconds, right? So we just don't have the measurement units. So that's why the continuous, we don't know the exactly equal to. So that's why you cannot say your random variable exactly equal to some value. So this probability will be equal to 0, right? Because your random variables can be continuous divide, all right? So like, for the discrete, so if I want to find the probability, so for example, if this is 3, 4, 7, 8, right? So for the discrete, if I want to find the probabilities from 4 to 7, then you can just go to your probability distributions. So you can say x equal to 4 plus the probability x equal to 7, right? So, but how do I define a continuous? So the continuous random variables here, if you want to find the area, you want to find the probability for your random variable between 2 numbers A and B here. So in fact, really it's just you remember, right? So for the here, because of continuous random variables, right? So for the continuous random variable, I cannot do a table like this. So the continuous random variable, in fact, if you find their probability distributions, it will be what is some type of the curve, right? So the curve may be like this, or the curve maybe like this, depends, right? So it depends on what type of the functions here. So this is we define as f of x. This is we say this is f of x, right? So this is how do we define the probability? We call this a probability density function. So this is a probability density function. So we cannot just write a table to represent it anymore. So now if this is your x's, right? So if you want to find the probability between A and B, so really what is here? You are just trying to find the areas between these 2 points, right? So from your calculus, if you want to find the area, so what is that? It's integrations here, right? So it's the integration. So that's why you take the integration of the A to B and the f of x here. Then we come out with this very good series here. They tell you if x is a continuous random variable, so here, just like we mentioned here, for the continuous random variable, the probability of this random variable equal to any specific value is 0. So that's why, so if you say that x greater than or equal to A less than or equal to B, doesn't matter you have this equal sign or not. It's not going to make the differences, right? So that's why we say the probability x greater than or equal to A, less than or equal to B, it will be equal to probability x greater than or equal to A, or you don't want to have you don't want to have the equal signs of the B, that's fine, right? So that's why this is kind of a very key things here we need to remember, right? So when we talk about the discrete random variable, we have a true character, if you remember. So what are the true character? So we say the Px, every probability has to be greater than 0. So the same characteristic has to be true, for the continuous here. Then we also say for the discrete, right? So we also say for the discrete here, so what is here, if you add all the x value, the px, what is this one here? Well, this one has to be equal to 1. So when we transfer to continuous, that means you integrate, right? Because we know, find the probability, you really is just try to find the area under. That means when you integrate this, the whole thing has to be 1. So whatever you defined as f of x, so basically the area under the curve has to be 1, right? So that means this is the area under the f of x has to be 1. Has to be 1 if f of x is the PDF for some random variables, right? Okay, so those are the very, very key important parts here, right? So it's very similar like we did for the random variable, the discrete, right? So the continuous is just mimic that. And then instead of using the summations, like for the discrete, we always use the summations, right? So we use the summation here and here. Then for the continuous, what here? We take the integrations here, all right? So be careful for that. Okay, so now let's take a look here, right? Okay, so that's why when you take this class, I guess your school will always require you to finish Calculus 1, Calculus 2, right? Because we are going to use the integrations here. Okay, so now let's take a look at the problems here. Okay, so this problem here, let's say that if x has a probability density function, the lower f of x equal to the k equal to the negative 3x for x greater than 0, and I want to find the k, and also I want to find the probability here. So in here, Okay, so I want to just kind of write down the formulas here, right? So this is a kind of the review for your calculus. I'm not going to, so this one's here, this is e to the ax dx is here. I'm just going to write out the formula because this is not the calculus class. I assume you know those things. So this will be equal to the a to the e to the ax, right? So plus c is here. So that's why, so this is the formula you need to remember, or, you know, like in the calculus 2, you use a u sub and try to prove it. But like I say, I'm not going to go through the calculus part. I just assume you know the formulas here, right? So we're going to work on the statistic part here. Okay, so let's say x has a probability density functions here. I want to find the k. So remember, right, just like we did a discrete, you add all them together, has to be 1. So that means, what is here? That means if I integrate, so this is a k e to the negative 3x dx has to be equal to what? Has to be equal to 1. And what is the integration area I need to integrate here? Oh, my x is greater than 0, right? So when my x is greater than 0, so what I need to do? I need to do from 0 to where? To infinities here. All right, so now I can take the k out. So this is 0 to infinity. So this is e to the negative 3x dx equal what? Equal to 1. And then, like I said, we use the formula I just put here. So this will be the negative 3 e to the negative 3x, right? Then this is the definite integration. So you put an infinity and a 0. This one will be equal to 1. Okay, so now in here, you will say this is kind of like, this is a negative 1/3. Okay, well, you can take the negative, I guess you can take a negative 1/3 inside, outside, maybe make it easier. So this is 1/-1/3. Then the inside will be the e to the negative 3x and to the infinity to the 0. This is equal to 1, right? Okay, so this is a k to the negative 1/3. And then when the top, the infinity is here, and I just use this notation. I know this is not a good notation. So for the statistics, you know, for the calculus, you really need to use like a t and the t approach to infinity. But in here, just to simplify, you know, like I said, I'm not trying to teach the calculus, right? So it's minus e to the what? 0. This is equal to 1. So then here you have a k to the negative 1/3. So I know what happens here when this one's here, this is equal to what? 0, and this is e to the n power is what? Is 1. So this is negative 1 equal to 1. So that's why k over 3 equal to 1. So that's why I get a k equal to 3 here. Okay, so k equal to 3. So I solved the first ones here, the k equal to 3. Now I'm going to try to find the probability 0.5 to 1. So that's basically, I know, I better go to erase here. So here, that means probability 0.5 to x less than 1. So now, according to our definition, previous pages here, remember when you try to find the probabilities, you integrate here. Okay, so that means in here, I will have here, so it's a 0.5 to 1. So now I use my PDF. So it's 3 e to the negative 3x dx. Okay, so I'm going to do the same ways here. So this is the 3. Then this number, the integration will be negative 3 e to the negative 3x. Then you substitute the lower bound and the upper bounds here. Okay, so after I substitute here, I get is negative 1 over e to the cube and plus 1 over e to the 1.5 or 2/3, like 3/2 here. So if you put it into the calculator, it will give you 0.173 here. Okay. Like that's why in here you need to know a little bit about the integrations in order to do that. So this is the one how to use the PDFs, right? So be careful, make sure you know the differences, right? So this we call this the PDF, right? So it's a probability density functions here. Okay, so now let's take a look at the next ones here. The next one is we call is the cumulative distributions, right? So that we talk about this, in the discrete one, we call this a distribution function, or you can call it the cumulative distribution functions, right? So you can call it cumulative distribution function. So what is the notation we use here? We say this is the CDF, right? So the CDF is just like you add all the, like for discrete, you add all the up to the x. So for the continuous, that means you integrate all the way up to x here. So that means from negative infinity to the x, then you change your function to TDT because you're going to integrate to x here. Okay, so the theory number 6 is very, very important series here, right? So let's say if the lowercase fx and the uppercase are the probability density function and the CDF. So that means the probability of x from the A to B is equal to the FB minus FA here. And also, this is a very important, right? So that means by the fundamental theory of the calculus, if you take the, so like based on these ones here, what is the derivative of the capital F of x? Will just be the f of x, right? So if you take the derivative of a cumulative function, CDF, will be what? Will be your PDF. If you integrate the PDF, it will give you the CDFs here. So let's take a look at why this one is true here, right? So let me show you here. So for example, here. Okay, so let's see here. Okay, so if this is my functions here, right? And then, so this functions here, right? So this is my f of functions here. And so if I'm finding the f A to B, so this is A, this is B, right? So I'm going to find in this area. If you use the PDF, this area will be what? Is from the A to B, the f of x dx, right? So let's see, how do I know this is the CDF also? Okay, so the CDF is here. Now you will see here, right? So okay, so let's see here. If you're integrating, okay, so I'm going to use different colors, right? So if you integrate from the lower bound, the boom, 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 to here, right, to the F. So what is my red ones here? This one's here, this is my F of B. And then if I integrating, let's get a different color, okay, green one, from the here, right? So from the A, from the negative infinity to A. So this is a green area, right? So this is the f of A here, right? So that's why when you use the f of the B minus the f of the A, what is that? Will give you the probability x from the A to B. What is that? So that is the integration of the AB f of x dx here. All right, and in here they said we're going to video 1, stop here. No, we don't stop here. We need to finish the 2 extra problems. Then we stop here. All right. Okay. So did you get that? That's a super, super important, right? So this is continuous random variable. So if you take the derivative of the CDF, it will give you the PDF. If you integrate the PDF, it will give you the CDF here. All right. Okay, so now let's take a look at here. So let's say to continue from the number 1, I want to find the distribution functions here. Okay, so I want to find the distribution function for the x's here. Then let's reevaluate that. Okay, so this one's here. Let's see here. So the probability, so density function from the problem number 1 is here. Right, so they give you here, this is, we already figured the case 3, right? This is 3x, right? So this is when the x greater than 0, and this is 0, the otherwise. Okay, so remember when we did a discrete random variable, we also go to back and forth, right? Give the PDF, find the CDF, give it the CDF, find the PDF, right? So for the continuous, we're doing the same things here. So now I'm giving the PDF, and this one's here, I want to find the distribution function. So that means I'm trying to find the CDF, right? So the CDF here, so it's capital F of x, right? So it's the integrate from the lower bound, so it's 0 to the x's here, right? Then in here, the f of what? T dt is here. I need to change the variable because I cannot have a variable integrate here with the same limits here. That's just the notations, you know, need to be careful. So this will be C3e the negative 3t dt, right? So now integrate that. So this will be 3. So this is negative 3 e the negative 3t, right? Okay, then you have x over 0. Then you plug in the upper bound minus you plug in the lower bound, you will get is negative e negative 3x plus 1. So basically this is 1 minus e the negative 3x. Correct? So this one is, of course, x is greater than 0, right? Okay, so now we can write it, right? So we can write it, this is my f of x, right? So the f of x is here is going to be 0 if x is less than or equal to 0, right? So if you put the 0 here, right? So if you put the 0 here with 0, and then it will be this function is 1 over e to the 3x, right? So this is for the x greater than 0. So now I'm going to find the probability here, right? The x between 0.5 and 1. So remember from the previous, so it's fb minus f of a. So what is here? So that means we're going to have what? We're going to have f of the 1 minus f of what? 0.5. So now I just directly substitute to these formulas, right? So this is f of the 1. What is f of 1? So it's 1 minus e3. Minus, what is 0.5? So it's 1 minus e the what? 3 times 1/2, right? So it's 1.5. So that's why when you do that, you will get the same things here. So it's 1 over e to the 1.5 minus 1 over e to the 3, right? Okay, so the same things here, you get a 0.173 here. So did you see the differences here? So this one, I get the CDF, right? So this is the CDF. I use the CDF, I can find the probability. Now what we did previously, right, for these 6 problems here, I'm just using the integration part for the PDF, right? So you can get the probability either by using the CDF or by using the PDF. Okay, clear? Okay, so now let's take a look again. The last problem for this video, then we're really going to stop here, right? So in here, so let's say it here, right? So let's say I find the probability density function. That means I'm going to find the PDF, right? That means I'm going to find what? Lowercase f of x for the random variable, the CDF is given, right? So this is the givens here. This is the CDF here. All right. So now I'm going to find the, the PDFs, right? So remember, the PDF is the derivative of the CDF. So the derivative of here, the first part, 0 still is 0, right? So what is the derivative of x here? X is what? The derivative of what is 1, right? Now what is the derivative of here? The derivative of here is what? Is 0. Oh, so this is pretty easy. So I can say that my PDF is equal to this, right? My TDF is equal to 0 if x is less than or equal to 0. My TDF is 1 if x is from the 0 to 1 and f equal to 0 again. And what is here? So when x is greater than or equal to 1. Okay, so now let's take a look at the graph for the f of x. It's here, lowercase f of x is here. Okay. So this is x. So read this right now. I'm going to do. So this is the f of x or the values here, right? So this is zeros, right? So when okay, so this is 1. So when the 0 to 1, right? So it's 1. So this is 1. And greater than 0, less than 0 is 0. So this is my, so what is it? This is my PDF. So is it correct? I hope so. That means if you find the area under here, what is the areas here? It's 1s, right? So it's 1. That's good. So I know this is the truth here, right? So let's take a look at what is the PDF, it's the CDF graph looks like. Okay, so this is 1. This is 1, see here, right? So the capital F of x, right? So this is the CDF. When x less than or equal to 0 is 0. So this is f of x equal to x. So it's y equal to x. So this is the 1, right? Then greater than 1 is 1. So this graph here, this is the, we call this the CDF, right? So the CDF should be an increasing function because the CDF is you add the area, you continue integrating till the end of your, the distributions, right? So that's what happens here. So that's how do you find the PDF by giving a CDF here. Okay, so that's why I'm going to stop here for these videos. And we have a couple more problems. We have 3 more problems I want to talk about. So it's just more practice. And so let's talk about that into the next videos here. So the first 2 problems here are very, very fundamental, right? From the PDF switch to the CDF, from the CDF switch to the PDFs, right? So make sure you understand that if they do have integration and derivative relations here. Okay, that's it. And now, so let's take a break here and we will come back here for the second video to do more this CDF and the PDF problems, okay? So that's it. You have a good day and I talk to you later, okay?